Today we will discuss one very important rule of finding limits, that's called L'Hopital rule, and this L'Hopital rule is basically used when we are indeterminate form of a function. Like say, suppose I have to find function limit x tends to a fx by gx, okay, and fx also tends to 0 and gx also tends to 0 as x tends to a. So what is this? This is basically 0 by 0 form, okay. Now this is called an indeterminate form of the type 0 by 0. Now you would have seen this type of functions or questions earlier also, like we had found this limit x tends to 1 x square minus 1 by x minus 1, this is equal to 2. We had found we had solved this question earlier. How we can solve this? We can say that okay, x square minus 1 I can write as x plus 1 into x minus 1, and in denominator also you have x minus 1, you cancel this 2, so limit x tends to 1 x plus 1, that will be equal to 2. Similarly, we had found this limit also, sin x by x, using geometrical methods, and this sin x by x is also of the form 0 by 0. I have to find limit x tends to a fx by gx, where my fx is x square minus 4 and gx is x minus 2. If I draw this if I draw the graphs of these two functions, x square minus 4, that will be the blue line, something like this, and x minus 2 will be this straight line. Now you see, at x is equal to 2, both are 0. So x square minus 4 is also 0, this is also 0. Now I have to find limit of this thing at x is equal to 2. But the problem is that at x is equal to 2, both the function, both the numerator and the denominator, both have value 0. So I cannot substitute their values at x is equal to 2, because I will get this 0 by 0. So what is the second best possibility I have? So this blue curve at x is equal to 2 is having value 0, and the red one is also having value 0. Suppose I give you a curve, the red curve like this, and I tell you okay, what is the value of this function or this curve at say this point, and if somehow you are not able to find the value of function at this point, and this is the green line is the tangent to this red curve at this point, okay, then my proposition is the value of this function at this point can be approximated by this tangent. You see how? No matter what kind of curve you take, any kind of curve you draw like this or anything, and you take any particular point like this, what I am saying is once you zoom out this function, once you take a very powerful microscope and look at this point, ultimately there will be no difference between this arbitrary shaped curve and the tangent of that curve at that point. Basically, the tangent of a curve is the straight line approximation of that curve at that point. Now this may seem quite confusing to you. What I am saying is, take any curve. The only condition is that that curve should be differentiable, that it should not have something, these spikes kind of thing or cusp or anything. That curve should be smooth. And you take any point on that curve, you take a point here or here, and what you do, you take a microscope or you use the Microsoft Paint function, and you start zooming out on this point. What I am telling that around this point, around this cross, this curve, no matter what may be the shape of this arbitrary curve, it will appear to be a straight line. I am telling you, you can do it for any arbitrary shape, something like say this or this or this. You see what is happening here also, that at x is equal to 2, I cannot substitute the value of x square minus 4 and x minus 2, because I will be caught in this trap of 0 by 0. So what is the next best possibility? Suppose I tell you that okay, you go and find out what is the shape or feature or color of a man called Johnny, and somehow you are not able to locate that Johnny is traceless. But suppose I give you another information, extra information, that Johnny has got a twin brother also by name say Tony, okay. Now if somehow you are able to locate that Tony and you know that this Johnny and Tony were born with a time gap of say just 10 minutes or 5 minutes, and they look similar. You will say okay, I'm not able to locate and trace or find out Johnny, but something is better than nothing. Let's find out how does this Tony look like. I can say that okay, Tony is like this, so Johnny will also be similar to this. Exactly same thing I am doing here. At x is equal to 2, I cannot substitute this thing because I will be caught in this 0 by 0 trap. So what I do, I will substitute this curve. You see what is this? This is my x square minus 4, but it is looking like a straight line. This is my x-axis and this is my point 2. I have gone very close to 2. This is my 1.95, this is my 2.05. As I go closer and closer to any curve at any point, any curve will appear to me as a straight line. This is my fundamental proposition, that no matter what may be this curve, I have taken in this example x square minus 4, I take x to the power 17 minus x to the power 16 plus whatever, something like e to the power x also, I can take anything, and you take x is equal to 2. At this point x is equal to 2, this thing also, if you go very close to 2, it will appear to be a straight line. What straight line? That straight line will be tangent to this polynomial or tangent to this curve. So at x is equal to 2, what I have done, instead of x square minus 4 using the whole curve, I have gone very close to this point 2 and I have zoomed out. When I have zoomed out, I have found that actually this blue curve, it has become a straight line, and this straight line is nothing but the tangent of this curve, this blue curve at x is equal to 2. Okay, and this x minus 2 was anyway straight line since beginning, so there is no point in this. So I had to find the value of fx at 2 and gx at 2. Then I will say okay, I am not able to locate this Johnny, so let's work with this Tony. For finding this Tony, I will go a very small distance, say I will go a very small distance dx away from 2. What will be my value of my function at a distance dx, and what is the slope of this straight line? Slope is df by dx. Why? Because differential coefficient, slope of the tangent is df by dx, and I have gone a distance dx. So what will be this height? This height will be df. Similarly for gx, if I go a very small distance dx, so the value of this function will be dg, because it will be dg by dx into dx, it will be dg. So what I am telling, that instead of working with say f of x divided by g of x at x is equal to a, or x tending to a, that is at x is equal to a, in this case x is equal to 2, why not work with a value of the function f and g situated at a very close distance dx away from this a. I have gone a very small distance dx, so what will be this height? This height will be df, because this tangent, the slope is df by dx, this base is dx, so this will be df. Similarly this distance will be dg. So now what I can do, that limit x tends to a fx by gx, instead of working with fx and gx, I can work with df and dg, and this will be exact. Why it will be exact? Because as you take limit x tends to a, that is this x is tending to a or 2 in this case, so this approximation, although to begin with you can say that okay, this tangent, no matter how small this dx, this tangent is an approximation, granted it is an approximation, but when I take this limit x tends to a, that is when this dx becomes smaller and smaller, this approximation will be very close to the actual value. So this limit x tends to a df by dg, and this I can write as limit x tends to a df by dx divided by dg by dx. So ultimately I had to find this limit x tends to fx by gx, but I can, if I find f prime by g prime under limit x tends to a, so this will also be same as this limit. So in this L'Hopital theorem, what is actually we are doing, that if we are not able to work with the exact value of f and g at say point 2, let's work with an approximate value of f and g at point 2. Now what will be that approximate value? That approximate value I can find using this tangent line approximation, because any curve like this or this or this or this, any curve, if I have to find value say at this point, if I go very close to this cross point, this curve will appear to me as a straight line. What kind of straight line? That straight line is tangent to this curve. So instead of working with the original curve x square minus 4, I have worked with this blue straight line. So for limit x tends to a, fx by gx has become f prime by g prime limit x tends to a. Now this proof I have given using geometrical arguments. The same proof you can give using algebraic arguments also. L'Hopital rule by working backwards. You see f prime a by g prime a, what will be that? Limit x tends to a, fx minus fa divided by x minus a. This is the definition of f prime a. This is the definition of g prime a. So this is limit x tends to a, fx minus fa by x minus a, x minus a. I will cancel out this in numerator and denominator. I will get this thing. Now fa is 0, ga is 0. So this is fx minus 0 by gx minus 0. So this is same as limit x tends to a, fx by gx is same as f prime a by g prime. After this long derivation of L'Hopital rule, let's see the exact theorem of the L'Hopital rule. It says that suppose that f and g are differentiable functions on an open interval containing x is equal to a, except possibly at x is equal to a. This means that this theorem is even valid when your f prime a does not exist. Okay, and that limit x tends to a, fx is equal to 0 and gx is equal to 0. So if this limit exists, limit x tends to a, f prime x by g prime x exists, or if this limit is plus infinity or minus infinity, then we say that limit x tends to infinity, fx by gx is equal to limit x tends to a, f prime x by g prime x. Moreover, this statement is also true in the case of limit as x tends to a minus, x tends to a plus, x tends to minus infinity, or x tends to plus infinity. Only thing is this should be of the form 0 by 0. When it is of different form, then also we can solve it using some algebraic manipulations. So let's say some examples. Suppose I have to find 1 minus sin x by cos x. You take limit x tends to pi by 2, you differentiate numerator by denominator, you get minus cos x by minus sin x, you get answer as 0. Similarly, if you have to find limit x tends to 0, e to the power x minus 1 by x cube, you differentiate it, x cube you get ex here, 3x square, you get plus infinity. If you have to find limit x tends to 0, 1 minus cos x by x square, you get sin x by 2x is equal to cos x by 2 is equal to half. Now remember, this applying L'Hopital rule to limits that are not indeterminate forms can produce incorrect results. It's very important. Suppose you have to find limit x tend to 0, x plus 6 by x plus 2. Don't use L'Hopital rule because it is not of the 0 by 0 form. If you use it, you will get answer x plus 1, x plus 6 differential coefficient is 1. This is 1 by 1 is the will get as answer, which is the wrong answer, because limit x tends to 6, x plus x, limit x tends to 0, x plus 6 by x plus 2 is 3, not 1. So this L'Hopital rule should not be blindly used. First you have to check whether it is of the form 0 by 0 or not. In next slide we will show that it can be of infinity by infinity, or also there are different other forms of indeterminate form. In those cases also we can use L'Hopital rule. For example, you see this is the theorem of L'Hopital rule for the form infinity by infinity. Exactly the same thing. The theorem, the suppose that f and g are differentiable function on open interval containing x is equal to a, except possibly at x is equal to a. This meaning that even if the function is not differentiable at x is equal to a, I can use this theorem. Then the same thing, limit x tends to a, fx by gx will be limit x tends to a, f prime x by g prime x. And moreover, this statement is also true in the case of limit as x tends to a minus, x tends to a plus, x tends to minus infinity or plus infinity. Okay, now suppose I have to find limit x tends to infinity, x by e to the power x. It is infinity by infinity form. You differentiate, you will get 1 by e to the power x is equal to 0 is the answer. There are different other indeterminate forms also, like 0 to the power infinity. Now when you are getting say 0 to the power infinity or different other indeterminate forms, you try to convert it into either 0 by 0 or infinity by infinity, that is either this form or the form given in form discussed in previous slide. So suppose I have to find limit x tends to 0 x ln x. So I can write it as ln x by 1 by x, because now it is 0. Now this is as infinity by infinity form. So when you differentiate, you will get 1 by x by minus 1 by x square, then you get minus x, 0 is answer. Similarly, suppose 1 minus tan x into sec 2x, you bring it into this form 1 by sec 2x, that is cos 2x. So this becomes now 0 by 0 form, then you differentiate, you will get 1 as answer. Similarly, if the indeterminate form is say infinity minus infinity, this also you should convert it into 0 by 0 form, like say 1 by x minus 1 by sin x, then you bring it in this form. Now this is 0 by 0, you apply L'Hopital rule, you differentiate, you give sin x is cos x minus 1, this becomes sin x plus x cos x, you take x tends to 0 plus, you get 0 as the answer. There are other forms also, like 0 to the power 0, infinity to the power 0, 1 to the power infinity. In such forms, you should make use of the ln formula. That is, suppose you have to find y is equal to fx to the power gx, you take log, natural logarithm, then you will get ln y will be ln of this thing, then this gx will come out, gx will be here, then this ln fx. Now this can be made into either 0 by 0 form or infinity by infinity form. For example, suppose I have to find limit x tends to infinity x to the power 1 by x. I write fx is equal to x 1 by x, then ln fx will be ln of this thing, that is ln x by x. Now this ln, when I find limit of this thing, that is ln x by x, this is infinity by infinity form, x tends to infinity, this is infinity, this is infinity. So when I differentiate, it is 1 by x by 1, 0. So ln fx limit is 0, so fx limit will be, this is base e to the power 0 is equal to 1. Now why can I do this step, from this step to this step? Because this ln is a continuous function. Theorem of continuous function, that when this function is continuous, then this limit say x tending to 0, this limit operator I can take it inside. Okay, so limit x tending to 0 ln fx is equal to 0. When I take this inside, I will get ln limit x tending to 0 fx will be 0. So this whole thing, you see from here, I can take the limit inside. So this is the thing. So now I can write this whole thing as limit x tends to 0 fx will be e to the power 0 is equal to 1.